Yes. Well, hello everyone, and thank you for coming, and thank you for everyone online, and thank you to Datacraft to give me the opportunity to talk about a subject that consumes a lot of my time currently, but is very important, which is evaluating the environmental impacts of ML solutions projects. And especially today, we talk about it like how we are going to do it in the real life, like in real projects with real tools. Some words on myself and what I do exactly. I'm a lead data scientist at Alygne. We do ESG metrics and data for investors and consumers. ESG data, it's environmental, social, and corporate governance data on companies. I'm also a contributor at Boavizta, where I contribute to the tooling and the ML impact, and we'll have an opportunity to talk about it next. I'm also a contributor at Data for Good, and we'll have the opportunity to talk about it also. You can find me on LinkedIn and on GitHub if you want to contact me and keep in touch. First, a word on Boavizta, the main reason why I'm here today. Boavizta is a non-profit organization or association focused on ICT impacts, like assessing ICT impacts and making it simple for organizations by producing open source tools, methodologies, and data sets. Members are from organizations, researchers, and freelancers, and we connect with other groups like the Green Software Foundation and others to share our work. It's been 3 years that Boavizta exists, and I have been there more than 2 years, so part of the beginners people there. So what we will cover today, first I'll start with a little bit of context, just to understand why we are all here today and why it's important to assess environmental impact of AI. We'll talk about how to measure it in practice. We'll see how we should do it in practice if you have the time and theory. And we'll also see methodologies and tools to do it in the real world, because you will see that between theory and practice there is a world. Some context on ICT and global warming. First, I'm starting with ICT. What it is? It's basically digital technology. It's the word used in studies, for instance. It's information, communications, and technology, and it's basically on 3 pillars that are data centers and what's inside, networks, and end-user devices. The definition is a bit broad because end-user devices, it includes your smartphone, your computer, your desktop, but also your TV, and in some cases IoT. So it's a broad definition. And AI is part of the services that relies on these physical things, physical devices, and that's important to keep this in mind when we are evaluating impacts later. ICT on a global scale, so worldwide, GHG emissions was estimated in 2020 to be between 2.1 and 3.9% of global GHG emissions compared to other sectors. The thing is that ICT is still a growing sector compared to some others, and it was estimated that in 2025 it will be between 6 and 8% of global GHG emissions. So that's why it's important to take a look at it today to try to reverse the trend and say, okay, we are intended to reduce GHG emissions, not to make it bigger. So it's important to keep that in mind, and ICT can have a big impact in that case. And we see it today with new services like ChatGPT. For instance, with this generative AI that we see pop up everywhere. We always talk about training these big AI models being bad for the environment. And that's true in some cases, but in fact, I want to emphasize on this. Using it, it's even worse we have modeled at Data for Good in a white paper the usage of ChatGPT for 1 month, and 1 month it's 20 times training the model. So if you are deploying models today in the wild, you have to keep that in mind too. If your model is very used, it will have a big impact too. And for those who don't speak like carbon emissions language, that's about more than 8,000 times Paris to Bordeaux by train, so train in France. It's about 1 year of the connection between Paris and Bordeaux. So consumed in 1 month of ChatGPT. And that's not very aligned with what we should do right now, which the IPCC is very clear on that. We need to reduce GHG emissions now if we don't want to suffer the consequences. So thus, this presentation to focus on how we can measure and reduce AI impact. And that's not the whole story. In fact, we talk a lot about energy consumption and GHG emissions, but in fact, the impacts of ICT, it's not only that. You have e-waste, so basically what you do with the device when it's dead, when you cannot use it anymore. Maybe you bring it back to the store, but what's going on after? Is it recycled or not? Well, spoiler, usually no. It ends up in landfills in other countries so that we don't see it, but it's still there. There is a huge consumption of water as well, both in the manufacturing when we make computers, but also when we use it. That's the part for data centers where we cool servers, for instance, with water. We use water there too. Natural resources extraction, that's pretty much using metals and minerals to make these devices that can be intensive too. And biodiversity loss can happen like in any step of the chain. If we have a warmer climate, then it's impacting biodiversity. If we are using too much water, it's impacting biodiversity. Well, it kind of takes place everywhere and every step of the process. And there is one methodology to account for all of that, which is called LCA, Life Cycle Assessment. In its version where it's multi-steps and multi-criteria. Multi-steps because we need to account for resource extraction up to manufacturing, then transportation, usage, and finally recycling, disposal of the ICT, the technology that you're using. And we see why multi-steps is important. Take, for instance, one server that you buy and you put in that you want to put in your data center. When you receive it, it already has an impact because we need to produce it. It's called usually embodied impact. So it takes into account resource extraction, manufacturing, and transportation to the end use location. And from that, you see the curve. You're going to use that server and the impact is growing, growing, growing. Of course, you're using electricity. So you're emitting carbon emissions, for instance. And the question is, if you have one server, maybe you want to replace it with the next generation. Like next year, you have I don't know, NVIDIA DGX H100, and you say, oh my God, it's the best chip ever. Maybe you want to replace it. Well, think about it before replacing it, because having something that is more power efficient, does it mean the impact is going to be better? If the embodied impacts are bigger at the start, you see here, to make server B that is maybe more power efficient, like worth in terms of environmental impacts, well, you need to keep it 7 years. 7 years in IT can be very long. So it's a real decision that you have to take if you want to replace a server, for instance, but it's the same for every devices, in fact. The usage part is not the only thing. You have to account for the rest of the cycle. And then why multi-criteria LCA? Well, it's important because if you only look at energy consumption and greenhouse gas effect, of course, you will find ways to reduce them. You can not buy server B that we showed before, or we can optimize the usage, like putting more services in one server and making more productive that way, and so on. Or we can use renewable energies in our data center, for instance. But if you don't look at other impacts, maybe you're optimizing greenhouse gas emissions, but maybe you're increasing all the other impacts. And what you do in that case, it's called pollution shifting. You're reducing one dimension, but maybe the other dimensions are growing and the impact can be worse in other dimensions. And finally, on the context part of this presentation, I want to talk about like the state of environmental impact studies in the ICT domain. You see on the top, we have data centers, networks, and user devices that I've showed you before. And on the side, the different steps where we can look at the impacts. Basically, today, what we see in studies and what we do, it's usage of data centers. The rest is just usually not covered. The embedded or embodied impacts are very rarely integrated because they are complicated, but there are some data. So we should tend to include them more for data centers, for instance. Networks are like complicated in itself, so it's complicated to have impacts. It's very difficult to compute anything, even for the usage part. End user devices, usually it's manufacturer data. So it's Samsung, Apple, and any other that will give you information, but usually you have one number. You don't have the methodology. So you cannot compare them because you can have, let's say, one phone with 100 kilograms of CO2 and the other one with 1,000, and you cannot explain why it's so much different. And it can depend on the methodologies. And if it's not open source, you cannot understand the impact. And finally, the end of life, it's just something that we see very rarely in studies. So there is very few information, and at Boavizta, we don't have any way to compute impacts for these steps. With one caveat for data centers, usually we see energy consumption and GHG emissions. That's the most famous indicators, but we don't see other indicators like resource extraction and so on. So that's also something we need to look on. It's not perfect on that side too. So when we know that, how exactly are we going to measure environmental impacts? And precisely for ICT. And in fact, there's a first catch here. At Boavizta, we prefer to use the word evaluate. Measurement is about precision, usually. Like you can measure temperature and it's a physical thing. You have a sensor and you have a precision on that measure. We prefer to talk about evaluation because the error bars are so much bigger practically. So you cannot like say it's a precise thing, a precise number. You cannot like compare with a lot of like numbers behind the comma or the dot. It's just not a process that is precise. So we usually talk about evaluation instead of measurement. So first thing, the easiest, how we account for energy consumption and electricity in the case of ICT. If you are able to monitor power through time, you can compute energy, just integrate the curve between a sample of time, and you will get energy. And with some impact factors, you can get to directly the impacts in terms of GHG emissions, natural resources extraction, water usage, and so on. These impact factors will depend on the way we are producing electricity. So it's not the same it's not the same per location. In France, we have nuclear power and other ways to produce energy. It's not the same in other countries. And it will also depend on the time. Of course, during the day, you can have renewables energies like solar panels, or when it's windy, you will have wind power as well. That will change the impact of electricity production. If you don't already know, there is a cool website you can check out, which is called Electricity Maps, where you have like a map of the world and every country colored based on their carbon intensity. And you can see exactly what type of power generation is used and what's the impact. It only accounts for GHG emissions, but it's a good way to start. That's the simple part of electricity consumption. Then there is the embodied impacts. And at Boavizta, we have built methodologies on that. Basically, if you can give us hardware specifications, we are able, with some formulas and some things that I will detail, we are able to compute environmental impacts, again, in GHG emissions, natural resources, extraction, and so on. Basically, to give you one example, hardware specifications, if we take a CPU, for instance, so if you've ever seen a CPU, it's a small rectangle thing that you put on your motherboard. You have some connectors that are in gold. You have a packaging in metal above the CPU. And in the inside, you have the die. This is basically the silicium that is containing all the transistors and make the computation. If you give us the die size of your CPU, we are able to compute impacts. Of course, tomorrow, if you have a server or laptop and you ask yourself, what's my die size? You will have a hard time to answer that question. So we also have databases and ways to estimate the die size of the CPU based on the model you have. So you would just say, okay, I have Intel i9 CPU, then we will be able to have the die size or approximation of it and then compute the impacts. This is a project that is called Boavizta API that you can check online. It's fully open source and you can get the formulas. It's not a black box. You can understand what's going on under the hood to understand how we compute impacts. And remember, it's for embodied impacts, resource extraction, manufacturing, transportation. There is no talk about end of life in this case. And as I said, end of life, we basically have no information. There are some studies, but very few. And there is no proxies or formulas that are easy to apply in the same way we've done with the embodied impacts. So right now, it's just a question mark. So we talk about ICT environmental impacts, but what about AI especially? AI is not computer, it's not hardware, it's a software running on hardware. How we can manage that? Basically, you can see it through the scope of your project or your ML project lifecycle, on top of the services and on top of the hardware you're using. Let's start with the data phase. Maybe you're going to, I don't know, train a sentiment analysis. So based on text, you're going to give a sentiment on the text, if it's positive or negative. It can be applied to tweets, for instance. Well, in the end, you will need data. You will need to collect data. So you need a network to access the data. You will need storage. So maybe hard drives, SSDs to store the data. Maybe you're going to pre-process that data. So you need compute. So you need powerful compute. So you also rely maybe on data centers. Going to the modeling phase. Maybe you're going to train or fine-tune a model, but that's the same. You're going to rely on computation, so you need a server, or maybe your laptop will be enough, but you will need hardware. And the same question for deployment. What type of hardware? I'm going to use a CPU, or I'm going to use a GPU for deployment. All these questions, you can put all these questions and say, okay, what's the hardware behind the scene? And what will be the consumptions of behind the scene of those decisions. But in fact, seeing the things like that can be complicated. First, because an ML project usually doesn't go that way, at least in my experience. There are multiple moments where you say, okay, we just go back a few steps before, or just the thing doesn't work, we start again. So if you on top need to have estimations of impacts, it can be even more complicated if the road is complicated on the way. And that's not finished. There are a lot of other reasons where impact assessment can be complicated. Maybe you are maybe there's a lack of expertise. You don't know how it works. So it takes time to understand how to monitor these impacts. Maybe you are sharing resources. You have one cluster. Okay, how to account for one project if everyone is using it at the same time. Maybe there is no global strategy in your company, or you need to promote these impact assessment methodologies internally to say, okay, no, it's important. We need to do that. And it can take time. And then there are some more discussions and so on. We will not cover all of these issues, but Boavizta tend to take all these issues and try to give practical answers for all of that. Today, we'll talk about tools, not how to convince people, for instance, but it's definitely a thing that you may need to do in your organization. So how we do it in the real world? That's the question we're asking today. I like to see it in the case of applied AI. So it's a particular case. It's not training like GPT-3 in a cluster. It's more you are in a company and you are making new features, for instance, on a product that is already existing. What I like to see to think of in this framework is to say it's data science powered by software engineering, seeing data science projects like software engineering projects, and trying to meet the both and say, okay, we're going to apply some methodologies of software engineering in the data science world to make those measurement of impact. Basically, it's we can split it in 3 phases, and maybe you will find examples in previous projects of where these phases are related to the project lifecycle in previous projects. One is the development phase. That's basically your playground. You're probably doing some prototyping. You're doing Jupyter notebooks. You're training models, maybe. You're working on data pipelines, because models are not the only thing in data science. Basically, there is a lot of work, and you're going on your laptop or maybe in the cloud, but usually working alone or in a team of data scientists. Then there is the validation phase. It's okay, you have your sentiment analysis pipeline, and you have your model, and you want to keep track of your model performance in time. Maybe you're going to retrain it, or maybe you're going to release new versions, or you can keep track of the quality of your model, and at the same time of the environmental impacts. And then there is the production phase. Your model is in production, it's working, the feature is working. How to monitor impacts in that case too. So let's start with the development phase. One tool I like to present you is Code Carbon. So if you're there and you're sensible to that subject, you maybe have already heard about it. Code Carbon will enable you to track electricity consumption and GHG emissions right in your code, right when you're running your code. It's as simple as shown on the right. So you install the library, you import it in your code, and you have like this object emissions tracker. And you can put, for instance, a training loop. You can put an inference loop on the test data set, for instance, between the start and stop tracker. And within this code, this block code, Code Carbon will monitor for electricity and then convert this into GHG emissions. It also integrates a dashboard for monitoring your experiments. So if you want to keep track of different experimentations, it's built in. I've already said it, but it's Python code, and it works in Jupyter Notebook, so it's quite good for data scientists use cases. And also, one important thing, it runs on most platforms. Like you probably will not have a hard time like installing it and making it work. We'll see that just after. So it's a good, it's one of the key quality of this software, and it's open source as well, like all the tools I'm going to present. So how it works in the background compared to the methodology that I have explained just before. Code Carbon is just a library that is going to talk with other lower level APIs on your system. There are at least 3 of them that are famous. There is RAPL, running average power limit. It's an API that will query for CPU and RAM energy and power consumption in real time. This is something developed by, I think, Intel and AMD. So it works on multiple CPUs. And depending on your system, the scope can vary. Sometimes you have CPU and RAM, and sometimes you can have more. It depends really on the CPU and the generation. You have NVML, which is a tool from NVIDIA to monitor GPUs that can report for power consumption in real time. And finally, there is Intel Power Gadget. And it's really important that it's here because it will enable Code Carbon to work on Windows and Mac OS. RAPL is not a software, is a software that is available on Unix or Linux OSs. But to make it run on Mac OS or Windows, it can be really challenging. You need to install drivers, it can be a mess. Intel Power Gadget can simplify that. And Code Carbon talks to Intel Power Gadget. So you will be able to make it run on your laptop, for instance. And getting the energy consumption like before, you just use impact factors to compute GHG emissions. In the case of Code Carbon, impact factors are basically coming from a static database that has registered for a country an impact factor, an average on the year. Or you can plug it directly using an API from HSC Maps that I already talked about to have more granular data and also real-time data if you want, if it's a use case, if you want to account more precisely for GHG emissions, for instance. And how to use it in practice, like what you can do. You can measure GHG emissions, but for what? One use case, it's comparing models. If it runs on your laptop and you can try one model A and model B, you will monitor for accuracy, for instance, to choose between the 2 models. Well, then with Code Carbon, you can add a new metric, environmental impacts, to compare those models. And you say, okay, you have, for instance, model A that has a good accuracy, and model B that has 2% better, but 15% more impact. Well, you can now then ask yourself that question: are those 2% accuracy worth the environmental impact increase? With Code Carbon, you can monitor that. You can also choose the best infrastructure to support your workload. So both while you are working, but in the future, when you are deploying your model, for instance, by choosing the right cloud region, for instance, if you're making your computation in France instead of United States, for instance. And also what type of hardware am I going to run my model on CPU or on GPU? Does that make a change in the impacts? That's important to check. Also, you can do carbon accounting, or at least simplify it. If your organization is asking your team to report for carbon emissions of your projects, well, it's a perfect tool to track them and just give a number at the end without taking too much time. And finally, you can integrate in any experiment tracking tools. It's just, again, one metric to report, just like you're already reporting for accuracy or any other type of metrics in the ML systems. Let's deep dive in a quick demo to show you how it works. Oh. If I can escape, okay. So we'll see a demo. Hope everyone can read everything. If not, tell me if there is an issue. So here I have a project with 2 models, a BERT1 and a DistilBERT1, and a data set. We'll use a test data set here. And we are doing sentiment analysis. So we have text and a label, binary classification. 0, it's negative, so it's a negative review, and 1, it's positive, it's a positive review. And it's mostly movie reviews from IMDb, for instance, if you know the website. So very classical NLP task, a lot of models available to do that. And I want to compare my BERT model and distilled BERT model here. Well, I just need only that piece of code to compare both of them. Loading my data, loading my models, loading the emission tracker from Code Carbon. Then I'm just doing a loop where I'm keeping the predictions and for each row of my data sets. And finally, I will print the accuracy and the emissions. A very simple use case. If I run this script, so of course I've limited the size of the data set to avoid taking it too much time. We'll see if it's not too long. You see it started, and the logs here are from Code Carbon. It detects the platform I'm using, so here it's a Mac, and it detects my CPU and RAM, and it will monitor CPU and RAM usage at the same time. It also detects there is no GPU available here. And while it's running, you will get information on energy consumption for RAM and CPU. It just finished. You see, I get the accuracy of my model, this dataset, and I get the emissions in CO2. Because I'm based in France, Code Carbon will find my location and directly link it to the impact factor related to my location. If I try with the BERT model, unfortunately, I think it's going to take a little bit more time because it's a bigger model. So we just wait a little bit. Talking about the output of Code Carbon, you have a very simple, you can use it very fast. You just will have CSV at the end, where you get a timestamp, the project name, and the experiment ID. And you will get all the informations I've printed in the console about emissions. And you will also get the energy consumption per different CPU, RAM, and GPU if it's applied. So we wait just a little bit to get the second one just to see. And of course, if you don't have access to this kind of libraries, if Code Carbon doesn't work on your system, it's possible. Then a good metric also to monitor for impacts is just what time, how long it takes. If it takes too much, if it double the time, well, maybe the impact is double. Like you can get also practical like that. It just finished with an accuracy of a better accuracy, and I didn't remember how much the impact was just before. So if you remembered, it was there. So the first model here, it was about 0.03 grams of CO2. Of course, it's a very small data set here, and here it's a little bit bigger. What's cool with Code Carbon is that you can get, you can install an experiment server. Like it will, if you connect to that server, this CSV, this information in the CSV will get online into a server, so you can keep track of it. And I'm going to show you the demonstration server of Code Carbon. And you see here, you can have multiple organizations and then multiple projects within that organization, and have global information, how much energy, how much CO2 emissions for that project, and within a time range. You can add tags on the data to say, see here, you have the difference between running on a laptop and a desktop for that person. And you have experimentations here with the date and how much emissions it has been.
I'll go to questions from the line. And that's the data that are in this dashboard. It's coming from directly from the code when you add the line start tracker, or you have to do some configuration in the code to have the data in the dashboard.
Yes, no, that's what's cool about Code Carbon. It's embedded inside. So as long as you're doing tracker.stop and you have precise in the emissions tracker, something about like, okay, if I can find the parameter quickly, but yeah. I don't know if it will be able, but you can like put an API endpoint of your server, and then it will report on the server automatically. So that was our use case for Code Carbon. Here it was for inference. We can do it for training or anything, basically, or you can even do it for non-AI stuff. Like if it's a data pipeline and you're doing processing without AI, you can measure it that way too. It's not limited to AI.
Do you have any question online on the Code Carbon, or it was quite clear actually? Maybe you have any question?
Good.
No, let's continue.
Let's continue, yes. So that was Code Carbon. If I can get that. I don't know how to get it away. Okay, good. So that was about Code Carbon. If you look online, you will find a ton of other tools like Code Carbon. And I have a list that I try to keep updated. And Xavier, you did mention one that I haven't found. So it was Carbon AI a few months ago. Basically, they will be similar in the terms of how they work. There are variations on the model they're using, on the impact factors they are using, or on the scope they are tracking. What I recommend is start with Code Carbon because it's the one that is going to work on most platforms. So you will have less surprises if you try with Code Carbon. But if you have a precise use case, check all the other tools. They can maybe fit better on your use case. For instance, PowerJolar is not really targeted to ML systems, but it can work on Raspberry Pis. So if you have a use case with ARM processors and Raspberry Pis, then PowerJolar works out of the box. So that's it for tracking in code electricity consumption and GHG emissions. There is another tool that can track also electricity consumption, but it's not the main focus of it. It's not the main purpose. This can optimize energy consumption, and it's only during model training. And precisely, I think it's more targeted to heavy training. Like if you're fine-tuning a model, like 1, 2, 3 epochs, it's not like relevant to use it. But if you're training a BERT model, for instance, it can be relevant. And we'll see how it does it very quickly after. There is also an extension to enable, and I really like it. It's like really buzzwords out there, but carbon-aware model training. What it means, it's if you are doing recurrent training, for instance, a BERT model, you maybe want to update it regularly on your data every month or every weeks, then you can use this to program the best timing to run that recurrent training. And it will use the optimization done in the previous trainings to the new training. Basically, you could do that by yourself, just looking at electricity maps and seeing where there is the lowest impact in your region. But here, you can have an extension that does it automatically. It will choose the best timing automatically. It's still Python code, open source, and there's one caveat for now. It only works on single node GPU training, so you need GPUs, and you need one server. You cannot do multi-server training for now. You can still have multi-GPUs on the server. So you can have 1, 2, 3, 4, and more GPUs on one server, but no multiple servers for now. And you see on the side, it works similarly to Code Carbon. You basically instantiate an object and you have this begin and stop window. And here you can define more precise measurement, like measuring an epoch, measuring some, you can get in the details with that library too. How it works very quickly, I'm not going into the details, there is a paper to explain it, but just to get a sense of how it works. Today, we are doing what's called in the paper TTA, time to accuracy. Basically, it's training your model as fast as possible to get the best accuracy. Like, just get faster and faster and you get your model trained and completed. Here, it's to try to optimize not time to accuracy, but energy to accuracy. So getting the model trained in not too much time, but with the lowest energy possible. And it does that. We're looking at, in fact, the ETA, it's the energy that you're going to consume to train your model, looking at the number of epochs, so how many training loop you're doing, the time, the average time of an epoch, and the average power of the GPUs on your system. What does this? It can act on the GPUs and setting a new power limit. Basically, a GPU, maybe it works at 200 watts, and it can take that range of power, and it will take as much as it can to run your computation. It's like automated inside the GPU. But there is an API to limit that power. You say, okay, you now are limited to 150 watts. So your GPU will run lower, but with less power. And you can also optimize the batch size. Choosing the best batch size against your hardware will change epoch time, number of epochs in your process. And using these two parameters with single optimizers, we can find on the Pareto frontier the best combination of batch size and power limit. And this optimization happens online. Like you don't have to choose or find the best combination. It's the tool that is doing it while you're running your training. So at the beginning of the training, it will try different power limits and different batch size and combine that data so that when it finds the optimum, for the rest of the training, it will stay at, for instance, a batch size of 48 and a power limit of 150. In the paper, they tested it on some models, and you can get from 24 to up to 75% energy reduction. So it's definitely worth checking if you are doing training of big models. And you basically just need to implement the library. It's like free energy reduction that you can get from this tool. If there is no question on that tool, I don't have a demo I don't have a GPU available and training, and it will take much time.
That's interesting because you have your large models, and you run in the evening, you go to bed, and the morning you have your model. Most of the time, as you said, that's the time we are looking at, and not the energy consumption. Yeah, you can set the energy consumption, so because you
can optimize on it. And it's really interesting for recurrent retraining, like because the model can, the library can save the data about the past training and just reuse the optimums and the testings that have been done to directly optimize the new training. And there is a cool video online. It's linked in the slides, so you can check a demonstration there. Now, I want to talk about the validation phase, what I call validation phase. Basically, it happens in CI pipelines or like CI pipelines lightly, where you are benchmarking your model. For instance, for QA, like quality assessment of your model, Well, while you're doing quality assessment, why not compute impacts at the same time? There is one tool that is still pretty much early stage, but we have working prototypes and it gets better and better every day. That is called software. It tracks many impacts, so energy consumption, GHG emissions, natural resource extractions, and primary energy consumption. It tracks them on the usage phase, like the tools before, but also on the embodied impacts. So it's the first tool that does this from the previous that I've shown. It's the first that takes into account the embodied impacts. And that's thanks to the Boavizta API that is embedded inside. Basically, what we are trying to do here is to make reproducible ecological benchmarks. You have your repository, you have a CI pipelines that can check for model quality, running a test data set, just like we've done with Code Carbon, but in the CI, to report on the dashboard, maybe the metrics of your model. Well, software can be installed on a server and just take your CI job and run it in a special environment to track for environmental impacts. And then what you can get in the output of software is a dashboard or a table with all the projects and the versions of your code with an impact. And you can check a revision of the code if you change something in your data pipeline, for instance, or just if you change the model. If you switch from a BERT to a Roberta, you have done your development, you see a better accuracy and so on. You choose to take that model, then you can track impacts here and have a single point to refer for impacts of each models and saved in your organization. It's still it's an open source tool and it's more a tool chain than a tool. It's not like software tool. It's combining multiple tools together to achieve that. And it integrates with GitLab CI today, but there's no real limitations. It could be other CI pipelines as long as you can run your CI pipeline on your server. You need a specific runner that can be in the software environment. And as long as you can reproduce that, you could use software. So how it works in practice. On your laptop, you have your code, model, and data sets. You can run training, you can run inference tests. Your code gets uploaded to GitLab or any version management systems. Models and data sets can be, for instance, referenced in DVC. DVC is a tool that on top of Git tracks your models and versions of your models and data sets. And they are all stored in, for instance, S3 buckets. That's an example. You could use something else. It's not embedded to software. And then comes software that is installed either on a server that you own or on bare metal in cloud. It will pull code, models, and information. And the key thing here is if you are using tools like DVC, it's very easy. You just do DVC pull and you get all the things that are attached to your code together, just like a Git pull. And it will run your CI job. And we'll see what kind of job we can run. While running the job, a tool inside software will monitor impacts in the CI runner of GitLab. When your job is finished, you will get some evaluation score, like the accuracy from your run, that will get that you can export. And you can export as well monitoring impacts, that gets published in a dashboard. Again, here you could use the dashboard of software that is currently in progress, so it's not very beautiful. It's currently a work in progress, but you could, as long as you get the data, you could upload it anywhere. In fact, it's not stuck inside software. And in practice, what it looks like to have a benchmark code. Well, it's very similar to what I've shown before. You just have a Python code that loads a data set. If you download it with DVC just before, a model with DVC just before, an inference loop where you use the data set and run predictions on it. You can compute any metrics that you want if you want, and that's the good thing. Like, you're free to do anything in that code, and you can do your quality assessment at the same time, so that you have both at the same time. And this code will get executed in the software runner, but via the GitLab CI. So you can run a standard .gitlab CI YAML file, and it's describing the how to install the project, and then run the benchmark that we just write here. So pip install requirements, DVC pool to get the models and data. There are two variables to get the start and the end of the process, and inside you run the benchmark. And finally, we have a script to just gather everything around and push it to the right dashboard and everything. And you need to run it on software, as I said, so you will probably need to put some tags in your CI to identify a specific server to run that code. And the output, as I said, it can be anything you like. It can be a table like that, where you can track different versions of a model or a data pipeline or just a project. If you're doing like your unit test, for instance, it could be applied to that too, where you get metrics like accuracy, F1 score, whatever. Throughput, there is also a metric that you would like to, that you may like to monitor for future deployments. And raw impacts on the right, you get CO2, ADP, and PU. I can get into details later if you want to understand exactly what are those values. And you can also construct your own impact score, like between 0 and 1, say, okay, is my model impactful or not? And have just one number to compare, just like accuracy, you can compare the accuracy between two models. Here you can have one value to compare your models in terms of impact. Again, we can talk definitions, how we do that. I don't have a slide of that, but it's very simple. And you can graph everything. If you like graphs, you can put them everywhere and track in time the evolution of your project. What's important here is to, like, it's good to have this kind of central point in your organization or in your team to monitor what's in production and what are the metrics. Like, you can keep them and they are stored somewhere. It's not just lost on the computer, on the CSV file of a collaborator, and you need to message on Slack and wait a few hours to get a response, and maybe the collaborator will not find the file or send the wrong one. Here, it's a central place where you get all the impact. So that's kind of that's something that can be useful for organizations. And let's do a quick demo here again. So I have in the same repository here, I have benchmark.py that really looks the same as the previous one with Code Carbon, but I have just removed the part with the emission tracker start and stop, but it's running the same inference loop here. And I can run the CI job. So let me just change the model here. So I put the BERT model here. I do a commit. So I say, okay, changed the model to BERT. I do a commit. I push my code. Takes a few seconds. Then I can get, just put that away. I can get on my repository that I've created here, demo data craft. You see my last commit. Here I have a small button because I have activated like manual launch of the CI jobs. It could be automatic, but here it's just me that I'm going to run it. I click on play on my benchmark job. And here you will get the logs of your model, like in any CI pipeline, and everything is happening not in the cloud, but on a server that is home, at my home, in fact. And it will get the code, install all the libraries, run the job, and I will get the measurements. Here, it's clearly not optimized. If you look at the CI pipeline, it reinstalls every libraries every time. So, of course, there are things you can optimize. Here it's a demonstrator. But I have here the previous one that I've used for the Distilbert model. And you see the execution. I have my benchmark here that run. I have the accuracy here in the logs. I also get a lot of information on the impact of that job that you can look directly in the logs of the job. And at the end, you have aggregated values. So global warming potential, it's CO2 emissions. It's just the usual way to name it in global studies, for instance. Abiotic resources depletion is natural resources extraction, how much resources you're using. And primary energy consumption, it relates to fossil fuels that you're using indirectly. And you have operational, so usage phase, what my algorithm used during the training, and embedded or embodied emissions, the two terms exist. This, you need to understand, it's fixed for a machine. Like you get the machine, it's as embedded impacts. Here, what's going on, it's taking the time you've used on that machine to attribute the impact of the machine to that job. Imagine your machine is 5 years, like the lifetime of the machine is 5 years. In 5 years, you know you're going to replace it. It's typically the duration of a server in a data center, for instance. Well, we take those 5 years and look at your job that is doing a small part of that 5 years, and we say, okay, a part of the emissions of that machine on the whole life cycle is for that small job. So you get a full scope emissions. And for instance, what it could change, it's here embedded emissions will depend on if you are using only CPU and RAM, or if you're using a GPU. If you cannot have a server without CPU and RAM, so you need them, but you can optionally have a GPU or not. If you choose to use the GPU, then the embodied impacts are bigger because you need to make the GPU before. That's why it's interesting to have this way to account. It's still installing dependencies, so maybe we'll see the result later. And so you get the output in the jobs log, but you get also a NoCoDB. So it's like Airtable, if you don't know. Basically, it's a table where you get all the jobs information, and you can add columns depending on your use case. And here you get the date, job ID, duration, the impacts here that are the same on my slide just before, and so on. And here, well, for this demo, we have an issue with the model accuracy reports, but you could add any metric that you want here with a working prototype. It's starting to run the benchmark. I think we can go on the presentation. Basically, it will just do the same, and it will add a new line here. And this first line was for Distilbert, and this one is for BERT. So we expect to have a longer duration job because it's a bigger model and bigger impacts in the end. Yeah, well, we'll get back to the presentation. We'll see at the end, maybe.
Do you have any question online?
Okay, so if yeah,
just one way. Do you Can we compare the software with Code Carbon? Do you have on the just electricity parts, is it comparable or not?
That's a good question. If you run it in software, you can compare them. And you will likely get the same results because it's using behind the scene the same APIs, RAPL, NVML, Intel Power Gadgets. So software is based on the next software that I'm going to show, which is Scafandr, and it's using the same API. So you will likely get a similar number. But if you're running it on your laptop versus on the server, of course, you will get different numbers. Because it's not the same hardware. So that's why it's cool to have one central place to get these impacts. Because if you are in team of many other data scientists, you don't all have the same hardware. Maybe someone has a Mac, someone has another computer running Windows, some other we have the next generation. So the numbers will always change, and you cannot compare between people because you will get energy that are different for all the computers. Here, if you're using always the same server with software, you get comparable and reproducible metrics for the impacts. Okay, so next step, it's the production phase. So you have trained your model, you have benchmarked it, and now you're talking maybe with the ops team to make it available and deploy the feature in your product. How to continue monitoring your impacts for your AI systems. One tool that you can use is called Scafandr, and it's supported by Hublot, which is a company that is very close to Boavizta. Scafandr is able to track electricity consumption, and it's especially for servers. And it's very versatile in terms of deployments and type of deployments that you're doing on your servers. You can run it on your server on bare metal. So you install it on your machine, and it will monitor electricity consumption. You can monitor electricity consumption per process. You can monitor a container. You can monitor a virtual machine. So it's very versatile in terms of use cases. And in the cloud, there are many use cases like that. And it's compatible with the latest container technologies like Kubernetes and so on. So it's interesting to have that. It's also a lightweight. It's all coded in Rust, and the idea it's very simple to install, and it doesn't take huge resources to make an electricity consumption to track this, because if it was an overhead, well, you could be spending energy for for nothing. And it can report this electricity consumption into monitoring tools like Prometheus, like time series database. You have connectors for that, and you can connect that to something like Grafana and get the power consumption in real time. It's really built for monitoring in the ops world, One caveat though, it doesn't support GPU for now. There's an issue on GitHub. It's a work in progress. But there is another tool that does it, that you can plug on a side Scafandr, which is called NVIDIA GPU Exporter. And this tool has the same exporters as Scafandr. So everything can go into Prometheus, and then from that you do your dashboards and everything. So you can use both of the tools to get a complete view of your server and electricity consumption. Scafandr will handle CPU, RAM, and more if available. And NVIDIA GPU Exporter will cover the GPU side. So how to use it in practice? I've spoiled it a little bit, but if you have inference services, a server, and it's likely you have it if you have big models, you can install it alongside other inference servers like Triton or anything. You can, with Scafandr, isolate processes, containers, virtual machines. So you can precisely report for one model, for instance, if it's run in a specific container, or one process in your container. It can be used also in training clusters, depending on the technology you're using. As it's very versatile, you can possibly install it in training clusters. You have to see with your admins. And thus, you can estimate precisely energy consumption, for instance, per inference of any model. If you have this kind of metrics for models, like you track throughput or latency of your model, well, you can combine that data with energy consumption and get an idea of what it is to host your model and what energy it consumes. And it can help you to define like what I call environmental-based usage limits, just like putting power limits on the GPU. Maybe you want to track energy usage and say, okay, at a certain point, I want to reduce the number of instances, and my clients will wait a little bit longer, but maybe it's not that bad. Like they can wait, maybe in some cases. You can like have more data to make this kind of decisions, and you can, in the end, get the environmental impact of taking such decisions, like getting bigger latency for your clients, using less servers, inference servers. Of course, it's negative for your clients, maybe, but they can maybe manage the weight. And at the end of the year, you could say, okay, I have done that. My clients are okay with that. And we have reduced the energy consumption and GHG emissions by that amount by doing that. So it can be interesting to do this kind of things and to have these tools to be able to put a number on the economy, the savings you're doing in terms of environmental impacts, and also the savings in the cloud. Let's be fair, less servers, it's less cost as well. I don't have a demo for that one, but you can check on the GitHub repo. There is, or actually, if we have a bit of time, we can. Oh, sorry. Okay, we can check it very quickly. What type of dashboard you can create? There is one that is publicly available at metrics.upload.org, and here you see the server is not not a lot used because it's very flat, but you get the host power consumption, and you can I don't know if this in this version, yes, you can see different services. Yeah, like there is a Redis database here, there is a Docker daemon, so you can put services here and see precisely per service what it's consuming in terms of power consumption and then energy. Okay, I'm getting back to the presentation. There is a bonus. It wasn't in the the first table of things that I've showed before, but I want to talk about scoping phase a little bit, because we've talked about how to measure in your project, but what about before doing the project? If you want to anticipate impacts, there are also tools to do that. There's green algorithms and ML CO2 impact. I prefer green algorithms. It's more recent and has better figures. These tools, you can just put your estimated or expected workload, saying I'm going to use a GPU for, I don't know, 100 hours, and it's that type of GPU. And you can have a calculation tool to give you impact. It's good to anticipate and plan ahead, but it's not enough to do impact assessment. Don't stop at this step, because there are caveats in in impact assessments. It's not that simple in practice, and these tools we see today, they are not perfect. So the formula here, it's even less perfect than using this tool. So it's good for anticipating, but not for accounting. You have other projects, and there's Boavizta API, where you can model hardware and workload usage. and get an impact just like the other two before. But here we can go much deeper into the modelization, and that's what we use in software, for instance. You can get very precise modelization of your workload, for instance, and get precise impacts. Precise in terms of evaluation, of course. It's not like measuring temperature, remember from the previous slides. And there is, it's an API that you can host yourself. There is a front end called Boavizta where you can play with some parameters. It doesn't account for all the complexity of how you can define workloads, but it gives you an example of how to use it. And finally, you can also take a look at studies. There are some that try to put frameworks on how to measure impacts of a project. And if you're doing that on the first project, it's going to get difficult. But if you do it on project 1, 2, 3, 4, you get better at this. And these papers can help you like getting the scope bigger each time, like covering model usage and energy consumption and so on, but also maybe data storage. We haven't talked about it before, but what's the impact of storing data? What's the impact of collecting data? Well, take a look at the papers. I have a list of papers that I try to keep updated as well. And this one that I've listed is basically a proposition of framework on how to assess impact for projects in AI. I don't know if there is questions on the scoping, but it was just to give some more information on impact assessment. Now I'm going to conclude. So what we have seen here, there's a lot of tools. They are tools to like get close and to give like an approximation of the methodology that I've explained at the beginning of how you can compute impacts. But even the methodologies at the beginning are not like real environmental impacts. It's not like measuring temperature. It's an evaluation. So it has big error bars, and keep that in mind when you're comparing numbers. Maybe sometimes you're comparing two things, but you're comparing the average, but the distribution of data that you could get on an impact is maybe 10x of the impact. So it's important to keep that in mind. As I've said just before, we haven't talked about data collection or annotation or storage or even networks. Networks are very complicated to take into account. We also, and there's also one message that we try to say at Boavizta. It's evaluating impact is difficult, even with all these tools. Like you will get like it's difficult to do it. It's a work. It's a job to do it, but it's not an excuse to start right now reducing the impact. And there are very simple things you can do to reduce the impact. Extending the longevity of the hardware you're using. If you buy a server, keep it 7, 10 years instead of 3 or 4. That's the same for laptops in your company. If you're changing laptops every 2 years, well, you could keep them longer. Limit the number of machines you're using. Maybe you don't need all that server. You can do more mutualization, or you can host more programs on one server, or you can use less programs. Sometimes it's less maintenance as well. So it's a double gain. And yes, and take the time to do simple optimization techniques. This is really, I don't see it everywhere, but if you're doing NLP and computer vision and you're using Hugging Face tools, there are amazing libraries to reduce the size of your models with just like a CLI tool. You just put your CLI, you put the place your model, and you get a free optimization with low impact on accuracy. So please try to do that. You will reduce the impact of your models very easily. And if you have CI benchmarks on quality assessment, you can do that and check that the new model that is optimized is still meeting your quality assessment metrics. And for Hugging Face, it's Optimum, the library, if anyone wants to check this out. And don't wait. That's the message. Another message. You can act on small things, like I've said before, but don't wait to integrate Code Carbon. It's one pip install away from your workflow and one few lines of code. So please try it and make it there. Maybe you're not getting the data. Maybe you're just like, it's on a computer and you see the logs and you see the CSV, but you're not really using it. But at least making the effort to like put it in your workflow and progressively integrate it into multiple tools and projects. Share your experience online. That's very important too, because you're not the only one to have these issues. The minimum is writing a blog post, I would say. Like if you're trying to make impact assessment in your company, try to share experiments, share your experiments and share your issues with it. And if you're making tools or methodology, consider open sourcing it. It's really important to get open source methodologies and tools. The example of taking, for instance, the example before, you have a smartphone that is made from Apple and Samsung. If you just get a number of like GHG emissions and no methodology behind, you cannot really compare them because the methodology can be so different behind that the impact it's not relevant to compare them. Do transparent accounting. So that goes with the methodology part and being open source. If you don't open source it, at least try to describe it before just putting numbers of carbon emissions. And finally, if you want I encourage you to join working groups and communities like Boavizta or the Green Software Foundation and others to get more information. At Boavizta, we have like a big knowledge database of things. We have we're creating an LCA workshop to understand how to make LCA impacts assessment and so on. So try to get in touch with these communities. They have great resources that sometimes are difficult to advertise. At Boavizta, there's no employee. It's an association. There is not very much money as well. So try go there and knock on the door and participate. And you will find great people and things for your organization. And finally, it's the last slide here. We haven't talked about indirect impacts and rebound effects, and that's even more important than everything we've talked about today. Indirect impacts, it's about for what are you using AI? If you're using AI, for instance, boosting ads and the selling of some products, maybe that's not really great for the planet. Or if you're using AI to make it easy for, I don't know, Total Energy to find new oil on the earth, on the ground of the earth, maybe it's not that great too. But AI is not only bad, there are good projects, and I encourage you to look at Data for Good. There are great projects there. The one that is from there, and it's from Pioneer, and it's early detection of forest fires. There are cameras to check for on forests that exist today, and they are making small algorithms to detect if there is a fire going on or not. So you don't have to have human checking on the cameras, on all the cameras, and you can have like a tool that detects if you see smokes, for instance, things like that. Well, the algorithm has learned that, hopefully. And there's the rebound effects. So does integration of AI or the optimization of AI models going to drive up the product or service usage? One example that I like, it's with video conference. Now, if you go on Google Meet, you get speech to text in real time with translation. So that's a great tool. But if it leads to every meeting with translation, with transcription, translation, maybe AI summaries using LLMs and so on, you have to question, do we really need all of that? Is it really useful? Or do we need it for every meeting? Like, do we need to activate it for every meeting? Think about the usage of AI you're doing. And this is a rebound effect because a few years ago, we couldn't do that because it was too expensive to run the model online on the video conference. But now we have made optimization, so it's possible to do it. Doesn't mean you need to do it. But then that's not necessarily a bad thing. That's the last example. Maybe this kind of technologies can help with inclusivity. Like if you can't hear correctly everything in the meeting, maybe reading the meeting, it's easier. And in real time, it's great for inclusivity for people with hearing loss, for instance. So not everything is bad, not everything is good, but try to keep that in mind. It's good for your job and for the projects you're working on. That's it. That's the final word.
Thank you very much, Samuel. Does anybody have any question on the presentation, on the tools?
I have a question.
Yeah.
Yes.
Does any of the tools give any information on the errors? Like
yeah, error bars. Yep. I don't think it's the case for Code Carbon, for instance, the first tools that I've showed for development phase. Software doesn't display them, but it's possible. Because in Boavizta API, we are currently releasing that, so it's a very fresh news. We are releasing error bars, not on everything, like computation of the impacts is, as I explained in the slide with embodied impacts and our specification. You give us your model of CPU and we give you an impact. We have errors, for instance, in the modeling, like you say, you have an Intel i5. Okay, we are going to estimate die size to estimate the impact. We can make errors on the die size as well on the impact. And we are currently giving error bars for this type of errors because we know how to compute them. For impact factors, it gets even more complicated because there's not enough studies to get error bars. Like we are based on one very good study from the Humboldt Forum. It's a Berlin German institution. But we just have, we have impacts, we have a column, but we don't have error bars. And to make error bars on impact factors, we would need different studies of the same thing on the same scope. And today's it doesn't really exist. So it's really rare to have them, but we are eager to implement them.